Now, hi everyone. Thank you for coming, first of all. And yes, I'm Elena Lazovik, and I'm stand here to present Dynamic Spark library. So, first of all, about myself. I am a scientist and innovator in TNO, which is Applied Research Organization of the Netherlands. So we have many directions in TNO, I mean not only IT, all the directions, and we work together to solve complex problems for industry in collaboration with the universities as well. So my typical projects are in big data, and why? Because I'm a part of monitoring and control group, and we monitor and control different physical infrastructures. That could be something from earthquakes, check, with sensors, cooperative driving, so going to automated driving on the roads. It could be something like live monitoring of the pipes of water and gas. Could be something else, but typically what combines all the projects, sensors platforms, that means a lot of data, and that means all the steps from data gathering till data storage, till data processing and visualization. So I'm a part of it, and of course, for many projects, I came to Spark for distributed data processing. And what also combines all these projects and what is common is one problem. In all these projects, there is the problem that we receive new versions from some applications, from our data scientists, from our developers. And we have long-running applications or maybe permanent monitoring applications that we don't want to stop, and we want to change it in runtime, the Spark application. So we try to look to the solution. And to solve this problem, we have checked and started the collaboration with the University of Groningen in the Netherlands. And the work that I present today, it's a result of the research projects, master project of Michel Medem and Toon Albers, the students of the University of Groningen, which were under my supervision and supervision of my colleague Erik Langeus. And we have checked and we have dived into Spark internals to understand what we can do to change the applications in runtime. So let's first check what is default Spark application. What is the behavior? Typically, you have many servers where maybe you install your data sources. If we talk about databases, or maybe you have streaming data sources which would come. On top of that databases, you will install Spark, you will install master, and you will install workers on top of the databases. And then you can start your job. So you write your driver program for Spark, you start the job. When you start the job, every analysis worker receives the tasks, and they execute one task after another. So this is default Spark application. It's generated in design time, and after that you can't change anything. So when you want to change maybe this module 1 as every worker, you need to stop all application and start it again. Let's see what we try to achieve with the dynamic of the fly. We want when the job already started and you have this module 1, module 2 running on every worker, and then we receive the new version of module 1. We want that it goes to the master, to job start, and then from that one, it goes to every worker, and it takes the place of the old model in runtime. For now, I hope it's clear what we want to achieve. So it's not enough. We want to do the same with the data sources. Because, for example, if we have sensors as the data sources, we don't want to stop the whole application when we add one more sensor to the 1,000 already working. So, of course, we would like also to check how to add new data sources or switch data sources in runtime as well. So we checked both these applications, and now you can ask why is it needed. Actually, it's needed for many kinds of jobs. From, of course, real-time applications is obvious, because there's a high availability is a need. But also, for example, there are long-running jobs where you don't want to lose your progress. So here you see, for example, the earthquake coming. And if you stop just coincidentally your application for update, when earthquake comes, you miss it. You just miss it. You can't do anything without it. Or if you, for example, goes to and calculate the underground model of a very big piece of underground, and you are so far along with the calculations, and you don't want to lose the progress, when you want to change a tune just one parameter for one small calculation, you also wouldn't like to stop it. The same for control in smart house, for control system. Gas leakage, if it happens and you stop the application, hello, you are doomed. And the same for example, monitoring of offshore platforms. So there are many domains where it would be really a question. So now when we understand that maybe it's really needed, let's check a little bit more formal description. So given a Spark driver program written by a data scientist or some Spark user, we want to change a function or its parameter in a running scenario, and or we want to switch one data source to another without stopping the whole application. So what can we change? What we separate Spark functional steps and functional step content. So for us, Spark steps are map, reduce by key, all that Spark known functions. That are the functions that Spark uses to process the data. But also inside that map, or inside that reduce, there is a real function that makes the transformation, right? And that function typically is written by user. For example, very simple example of the transformation functions x to x plus 1. But then data scientist, for example, comes and says, oh, sorry, it should be plus 2, not plus 1. So we thought, okay, it's written by user, so maybe indeed in this arrow where we put the content to the map, we can inject our functionality to change in runtime. So we checked some strategies. There, of course, for Spark program could be two strategies that master would push the changes to workers, or also the workers could pull the changes from master. When the master pushes the changes to the worker, it's very interesting, but it's very hard to implement, since what we have seen, first of all, the task goes to worker. The worker executor doesn't understand that it's update. It just takes it as a new task. So how to recognize it? It would be maybe useful to rewrite the whole Spark scheduler. We don't want it. We want to have Spark. We are very happy with what Spark does. We want to have a library which sometimes let us to change the runtimes on top of Spark. So because of that, we have chosen pool variant. So the workers, when they come to the face of that function that could be maybe changed, they check if there is update. Let's see an example, very simple example. So here we have a very basic example where we have 1,000 numbers that we multiply and factor by 10 and make a total of it with the reduce function. We make it 100 times iterations and in 10 batches that you can see. So what we want to change is just that simple parameter. It's hard-coded for now. So how we introduce our library? Map that you have seen in the code becomes dynamicMap. So it's our, let's say, function. In place of maps, we have dynamicMap, we have dynamicReduce, we have dynamicFilter, dynamicReduce by key, and other functions. So here it becomes dynamicMap that takes a function, which is e multiplies on factor value, and factor the parameter. Actually, in our case, it's 10. To be able to do it, of course, we need to have that factor. So before, you see factor is a new parameter, which with version 1 and value 10. So how to receive the update? First, our solution was, okay, let's start small server, which would wait for the parameters which arrive. So maybe it's not, it's asynchronous call. So when it's needed, the call would start. And when the call is executed, so dynamicMap is responsible to check if there is a change of a parameter, and if dynamic server receives it, so dynamicMap checks, okay, there is a new version, I need to download new version, and I need to use that new version in the calculation. For user, that would mean, okay, factor, we have had factor there, right, with the version Z, we need just write new version. That's what user would write. The new version of factor, 15, for example. Let's see what's happened behind the curtains. What is the flow, actually? So there we have our worker with a dynamic map. We checks, okay, should I go to the update? Is it the dynamic map or is it the normal map? Okay, it's a map, let's go for update if there is a new version. Then, okay, if there is an update, I receive from master the new class, serialized class loader, which I can deserialize, store a new version, store the value, and use that value. So master, in its turn, receives the serialized object from user through REST server at this moment. It could be function, it could be very complex functionality model from some data expert, and it could be just some parameter. So actually, the function becomes also a parameter somehow for the dynamic map in this situation. So user makes new version, serializes it, puts it to the master. Master tries to deserialize it to check if it's okay, and then the workers would check if there is a new update. Let's see the code. So what's inside dynamic map? First of all, we use rep function. And this rep function takes a function, so it's that x plus 1, for example, to x plus 1, checks function, checks parameters, makes an update parameter calls, or function or parameter, or all of them together. And that update parameters you have seen earlier with the class loader. And then we have our dynamic map that uses this rep function to wrap the normal function. So actually, to normal map function goes already the wrapper. So and that wrapper is responsible for checking the new versions of the parameters or of the functions. And we have an implementation for dynamicReduce, dynamic filter, and many other functions. So how do you pass to the program that function? So it's actually, it's here, right? You can pass it as a reference function, so make a val. You can pass it as a method, so definition, here. Or you can generate it on the fly and pass it this as a parameter on the fly to the program. So the functions are passed as the parameters to the program. Now we have done some experiments to see, okay, we have this solution. What is the overhead? If it's quite big, maybe it's not interesting to use it. It was surprisingly good result, because we actually tried to check it with Monte Carlo algorithm. Here there is a limit state function which is in use for calculating reliability index, which we use for calculating probability chance of failure of some physical infrastructures, of pipes, of water and gas. So R and S, sorry, in these limit state functions are normally distributed functions. So and we just tried to change actually R and S functions in runtime. So here you see 3 scenarios. The first red is the normal scenario, so Spark without any dynamics. So for us it's basic. Let's see what Spark would do without our functionality. So for us it's 0% overhead. Then we checked the second variant is orange as a dynamic variant. So we have our functionality added, our library and our implementation to the driver program, but we don't update. So just what's the overhead? It's a little bit more than 1% of just having a library without any updates. And the third one is in time of update. It's an overhead in time of update, it's 11%. So when it doesn't update, it's just 1% overhead. It's very small, so you can allow it. And when you update, it's so it's bursty, and it's sometimes 11%. And we think that it's a very good result, because what we expected to tell you the truth is completely higher. So we were like, wow, very good. Then we turn to another problem, to data sources, because it's like the second part of our check. What do we do? Why do we need the dynamic switching of data sources? For example, our database could become unavailable because of the connection, because of server failure or whatever. So you need to maybe to go to another backup system of the same database. Or maybe you didn't have a data source with more accurate data, but then new data source arrived and you say, I want to use that in place of that old, which is maybe not so accurate. So you make a switch. Or maybe also I want to add new data source to my analysis. So the questions were, is it feasible? Is it possible? And what is the best approach if it's possible? To check is it feasible was very easy, because data sources are externals. so external program to Spark. So you could do actually, of course, something in between Spark and external program much more easily. So the question was answered yes, and check for the best approach. What are the approaches to implement the system that can switch to the data sources? So first, make an extension of Spark itself to check how it's possible with the Spark Data API. And second, to make an intermediary system, like specific system, like data access system, which would check all the data sources, change the data sources, and then the changed data comes to the Spark. We have implemented both to compare them. Of course, the performance is the first comparison criteria, but not only, because what's the easiness of use of every solution? Which solution is more flexible? Which is more efficient, not only in terms of performance, but also deployment, maintenance, what's easier? Also, which is more extensible? So we have taken all that criteria to compare these two approaches. So, of course, for every of that approach, for both of them, what you need to somehow access data in the format of the data source. You have native queries for that data source, and you need the data transformation maybe to prepare the data to come to Spark in the right format. That's the same for both approaches. That's what you should deal with. Also, the data locality, we still would preserve data locality. Spark is very smart. Spark tries to start the job where the data resides on that node. Exactly, we want the same. So, because it doesn't generate a lot of traffic. And when you have a lot of data, it's really an issue, especially for networks. So data locality should be there. Also deployment. How it should be deployed, especially with the case of intermediary system, what and in which manner should be deployed to guarantee data locality, to guarantee the access to heterogeneous data sources. So first, let's check extension API. So first, the Spark extension. So what you see in the middle here, it's what we add. So default situation, we have typically data source and data source relations, what you would call actually a Spark driver for some data source. But in Spark, it's called data source relation. And from another side, you have processing scenario of Spark. So what we try to add with our extension, we make new data source relation. It's actually access layer, which has indeed meta driver, so dynamic data source relation that has the communication with the selector of the data sources, and which in its turn has communication with the reader, which reader is responsible for translation and transformation the queries to native query source. Because if you talk to, for example, Hadoop system, it would be one format and one query. If you talk with Cassandra or something else, it would be completely different query. So that's what we added, actually. This is what we implemented. How have we implemented it? It was quite easy. We used Spark Data Source API. So there we needed two classes, relation provider. It's actually provide, let's say, the metadata of relation, and base relation, which is like native relation of the data source or driver. So let's see. First, relation provider. What it did cost, it was quite easy. We just, in relation provider, we overridden create relation method, where we create our dynamic data source relation in place of normal data relation, in place of normal driver. That's it for relation provider. And we have data source relation, so the driver, where we indeed should have our schema. So you see here that we have schema with timestamp and value, typical for sensor data, of course. For me, it's quite obvious. And we have overridden build scan method from data source relation, which also creates a selector. And selector selects the specific data source and then read exactly already from that data source. What it would, here you see two variants. The first variant in program, how it would look in program, in your program. The first is without dynamic Spark libraries, the second is with. So the only thing that changed is the last one, that you don't make RDD from text file, you make RDD, data frame from dynamic source. And here, inside the quotes, you write the name of your data source that you want to use. What's about intermediary system version? Here we have a little bit different approach, of course, because we should choose intermediary system. So we decided still we have the same data sources because we have made the tests for Cassandra and HDFS switch actually. And we used ACA streams as an intermediary system library because they have quite interesting concept and we can achieve more control on data locality with the ACA streams. So, and then ACA streams would send, so Cassandra and HDFS would switch through ACA streams, and then this already prepared data goes to Spark. So here, what you have seen as a Spark extension, here all that functionality of dealing with native drivers for data sources, dealing with the read and transformation of data sources, dealing with the iterators iterators through the data from the data source. It should be an intermediate system. So we implemented all that, and then we checked the results. So now here you see the results of the tests of two data sets, small data sets on that side and the larger data set. Small data sets around really small, 60,000 records, and another little bit larger, 33 millions. And what we checked, so you see first of all 3 scenarios for Cassandra. The first one is regular Spark Cassandra without dynamic. The second is the result of performance for Spark extension for Cassandra, and the third with intermediary system as a result. And the same for HDFS. So first, the red one is HDFS regular, then extension of HDFS, and HDFS with an intermediary system, how it performs. When you see it on the larger data set, you see it obviously, especially that Spark extension actually performs better. So the intermediate system adds much more, I mean, a very big layer of intercommunication between all of them, and it takes much more time for intermediary system to respond. However, at the same time, of course, intermediary system is interesting because if you have such intermediary component, you can choose, for example, another data processing engine or another data sources maybe, which are not so suitable for distributed data processing. So both of them are interesting, but we see here that the results are quite clear. Here, extension is much better. And actually, what in percentage, it was in average for a small data set, the extension of Spark overhead was around 11% for a big, let's say, bigger or larger data set. It was around 15% of overhead of having updated and switch of data source. And for intermediary system, it was 25% of changing the, let's say, of performance overhead. It was done in 6 Spark workers, yeah, maybe not so big cluster, but we saw that it's enough for preliminary tests. Our future work is actually to build an open source library, Dynamic Spark for Spark 2.0, because actually when we started, it was still Spark 1.6. And then with much better API, with the use of data sets and data frames instead of RDD. And also, of course, more tests are needed for streaming data, like real thousands of sensors checking what would be the overhead of the streaming data. And also more efficient, maybe dynamic code update, because right now we have chosen to have the REST server and REST invocation, but of course there could be the alternatives, how you could get the serialized classes to the system. So we should check the alternatives. Okay, thank you very much. I hope it's enough time for the questions.
Anyone have questions? Any questions?
Thanks for the speech. It was really interesting. I'm just curious. Couldn't we run into any potential version conflict of RTTs? If you are processing an RTT and suddenly you change the way you compute the RTT, aren't you creating like two different RTT lines? You know what I mean?
Again,
You have an RTT.
yes,
Okay, an RTT is made up of a series of steps.
of course.
Potentially, you might find that you have one generation of RTTs created with one specific set
Okay,
of
yes.
and another one.
Yes, that's we think actually about the question is about if what do we do, because maybe especially for permanent jobs, maybe that we have RDD created in time with the old code, and then in some moment we have an RDD created with the new code. How we manage that? We thought actually about adding the timestamp, so from which maybe the workers, all workers, would start work with the new code. Let's say that we also know the timestamps from which the new code is taken into consideration, and from which all the workers would take the new version into the work. We thought about timestamps. Okay.
Hello.
Hello.
Sorry, I missed the first part, but I noticed that the updating, it only concerned a parameter, not the
No, yes, that's
the
true.
code base.
True.
Ah.
But actually, what I have talked since, if I go again to that function, it's actually function. It also becomes a parameter for a wrap function, which is responsible for the update. So we see the function as a parameter. So you also can take it as a parameter. For you, it's a function, but for wrap function, it's a parameter. And then you just take it as parameter and then apply that parameter, so that function in your map or reduce function. That's how we deal with it.
Okay, so imagine that I have a big batch process of 5 hours, and I noticed the hour 4 there is a bug in my code. So there is some input data that doesn't correspond to my assumptions, and I want to quickly solve this and continue to run this last hour with the corrected code base. So would that be a use case that fits your solution?
I think so. Yes, definitely, because you can update it step by step, indeed, and your application will still be running, and you don't lose the progress. Of course, of course, you should guarantee that all the workers would start it at the same time. That's why we talk here about the timestamps, that every worker would try to start the new job. But yes, I think yes, you can do it. What's the most important here? Your application continues to run still, so you don't need to stop it.
Okay, thank you.
Yes, thanks.
Cool. Thanks, everyone. Thank you for the talk, Elena.
Thank you.
Oh, quick question. If they want to get this code, is that open source or?
Yes, that's what we plan indeed. Since it was a Spark 2.0 and we should rewrite some, let's say, questions, it will take some months, but we plan maybe in January to have such a library.
Awesome.
Open source.
Thanks.
Yep.
Thanks, everyone.
Thank you.